Hello everyone and welcome back to NL582, Modeling and Control of Electric Machines and Drives. In the last lecture we were continuing talking about the starting methods for three-phase induction motors, but at the end we started talking about a total different thing, which is actually the modes of operation of three-phase induction machine. Okay, like we said last time, we have three different modes of operation that our machine can work in. Firstly, the motor mode, which is the most obvious one, which is the mode we have been talking about all the time before. So the machine can work as a motor, which is mean you have an electric power input and mechanical power output, like any other kind of a motors. Actually, that's the definition of a motor, if you know. Like we said last time, refer back to the lecture if you don't remember, that basically for the machine to work as a motor, that means that is the synchronous speed direction. For example, the synchronous speed is the speed of magnetic field, because you know for a three-phase induction machine the magnetic field actually is a rotating magnetic field. That means the poles that's rotating around the circumference of the machine by the synchronous speed. Okay, for the motor mode, the rotor actual speed is the mechanical speed of the motor, which is the rotor body mechanical speed. So like you've seen, it is the same direction of the synchronous speed, which is obvious, because actually for the motor, the rotor just slips behind the magnetic field speed, like we just had before in the theory of operation of this kind of a machine. So that means the synchronous speed and the mechanical speed are in same direction, but the mechanical speed is slightly less than the synchronous speed. And that's why we want to calculate the slip for the motor modes. The slip equals ns minus nm over ns. So as the mechanical speed is less than the synchronous speed in the same direction, that means your slip for the motor mode is just higher than 0, less than 1. Okay, it will be 1 if the mechanical speed reaches the synchronous speed, and that will never happen, like we said before. And it will be just it will be 0 if this, and it will be 1 if it is no speed at all, if nm equals 0. Okay, and that's at the starting point of the machine. Okay, and like we said, for the power flow diagram of such mode, you have P input here as electric power going to the stator, obviously, because that's how the electric voltage goes into the machine. It goes to the stator terminals, and you start losing some copper losses in the stator. P copper losses 1, and you lose core losses both in the stator and the rotor. The rest crosses the air gap going to the rotor, which is the air gap power. You lose some of it as copper losses in the rotor, and the rest will be your converted power to the power converted from electric to mechanical form. And you lose some of it as rotational losses or friction bondage losses, whatever you want to call them, and the rest will be your output power, which is mechanical power. Okay, you know the electric power here goes to the stator side, and it is being converted to mechanical power by rotating the rotor. Okay guys, so that is the motor mode. I'm just trying to revise what we said last time, just to keep you on track. For the generator mode, which is the second mode of operation, generator mode, so our machine can work as a generator. Actually, how you do this, you get P electrical, or let me say, not call it like that, I'm gonna say electric voltage is connected to stator to build magnetic field, okay? That is by reactive power, Q, and mechanical power is placed on the rotor to push it higher speed than the synchronous speed. Like that, you will have a generation. You just put electric voltage on the stator to build your magnetic field, and then you just forcefully rotate the rotor, and this is your mechanical power going to the machine, which will be converted into electric power into the stator, okay? So doing this, you'll have a generation. So like we said, if this is your synchronous speed, which is the speed of the magnetic field, to have a generator, you have your mechanical speed of the rotor to be on the same direction but higher than the synchronous speed. Now you have a generation. So your mechanical speed has to be higher than the synchronous speed to enter the generation mode. And that means, again, if you want to calculate the slip, which is ns minus nm over ns, okay, you know now the mechanical speed is higher than the synchronous speed, and that means your slip for the generator mode will be negative. The slip will be less than 0. Negative value means your mechanical speed has just outrun your synchronous speed, and that's how you get generation, okay? For the power flow diagram, it will be just like any other kind of a generator. So the input power goes as mechanical power here, and it goes to the rotor like any kind of a generator. Your mechanical power goes through the rotor by rotating it, okay? You'll lose some rotational losses, and then the rest will be just converted into electricity, okay? That's still on the rotor. You'll lose copper losses on the rotor because there's current moving into the rotor winding, and then the rest, your air gap power, which crosses the air gap, going to the stator this time to be converted into electricity. Again, you lose core losses on the stator and copper losses on the stator, and then the rest will be your output power, which is electricity now, electric power. And that is now on the stator. That is how the power going on from the rotor now to the stator as mechanical power, okay? That is the active power, P. But like we said, Q, that the machine, like we said last time, for the induction machine, it does not have a separate winding to have separate source to just give it electricity to build its own magnetic field. It does not have a dedicated winding for excitation like synchronous machine, for example. Synchronous machine has the rotor winding we call the excitation winding. We just put DC voltage out there to build the machine's magnetic field. For the induction machine, the machine has just used the same winding, which is the stator winding, where you push the electric power into the grid. You use the same winding to get some reactive power from the grid to build its own magnetic field. So the induction machine alone like that will not be a source to just generate reactive power and push it to the grid. Actually, it gets it from the grid. And where to get from the grid? From other synchronous generators connected to the same grid, okay? Like I said last time, if you're not connected to a grid at all, you just work in an isolated mode, just feed in an isolated load, then you have to place capacitor banks at the terminals of the generator to give it the required reactive power to build its own magnetic field. Otherwise, it will not be able to generate electricity at all, okay? If you want to place this some sort of a numerical perspective, just to make it easier to understand, that's a numerical problem. You'll find it in Dr. Knight's online material. You can just follow along with me. So he's now giving you some data about an induction machine, a 480 volts, 60 hertz, 6 poles. Like we say all the time, 480 volts, that's the rated line-to-line voltage. Okay, so this guy is V line-to-line rated. 60 hertz zero frequency, 6 poles, number of poles, 3-phase delta connected, that is a connection, induction motor, or let me say just induction machine, okay? with the following parameters. He's giving you the equivalent circuit parameters are 1 or 2, x1, x2, and xm. And giving you rotational losses are 2450 watts. That is the P rotational. Okay. He didn't talk at all about the core losses, and that's why we just ignoring it, and doesn't give you anything about RC here. That means we're going with the approximate equivalent circuit. Okay. That is R1, JX1, and that is your JXM. That is JX2, and that is R2 over S, that is V1. Okay, keep that in mind because that is so important now. That is I1 and that is I2. That is the equivalent circuit of motor mode. Okay, because that's obvious. Okay, for doing like that, the current is coming from the supply, which is V1 here. That's your supply going into the machine. That happens just in motors, you know. For generators, this current should be reverse direction. The current should go out like that, because you know the generator gives electric power, gives the current to the grid, not taking current from the grid. Okay, that's why this notation here, just by having this like that here, that means this is the equivalent circuit of an induction motor, not induction generator. Okay, just keep that in mind, and we'll just know how this, just what this mean now. Okay guys, now suppose that the machine is being driven by a mechanical system. So you have a mechanical input, something that drives the rotor, such that it's rotating at 1224 RPMs. That is the actual speed of the rotor, Nm. He wants you to calculate him the slip, the line current, the active and reactive power at the terminals of the machine, the air gap power, the torque developed, mechanical power, and efficiency. It's just a normal problem like we solved problems before, just like it, with three-phase induction motors using the equivalent circuit. Yeah. So let's see how we just go with this. First of all, to calculate the slip, you need to calculate the synchronous speed. The synchronous speed calculated like 120 F over P. Okay, so you calculate it, you'll find it 1200 RPMs. Okay. To calculate the slip equals Ns minus Nm over Ns. You know that. That is Ns, and that is Nm given in the problem. Like you've seen here, Nm is higher than the synchronous speed, and that's how you have a generation. And that's why you're saying here this slip is negative, it's less than 0. So that is generator mode. Okay? That is how you designate the generator mode in the induction machine, if that's to have a negative slip. That means the mechanical speed is higher than the synchronous speed. Okay? To calculate the current, just go in the same way. You just plot the slip here, R2 over S. So you plot the slip here. I'll leave it negative because the slip is negative. And you just calculate the total impedance of the circuit normally, and just divide the voltage V1 by the total impedance, and you'll find the current. Okay, guys? If you want to just calculate the impedance, you will find it like that. And you just find the current, you know, it is just the current is basically V1 over the total impedance. Call it the input impedance or total impedance, whatever you want to call it. Okay? So like I said here, that is how you find I1. So he just found I1 by V1 over Z input or Z total. So the voltage 480 volts. Okay? We didn't transform it by dividing by square root of 3 because the machine is delta connected. Remember that. So the phase voltage, which is V1, equal the line to line voltage, which is given in the machine's ratings, divided by the impedance, which is minus 10.3 plus J 5.29, and this will give you this value here, minus 36.7 plus minus J 18.8. Okay, if you remember other problems when you solved about three-phase induction motors before, reverse out different ones, you will find that this real part of the current was always positive, not negative like that. What's indication of having a negative real part of the current? That means the current is reverse in direction. It's not going inside the machine like that, rather it's just going outside the machine because it's a generator. Okay, guys? You wanna just calculate the power, the active and reactive power of the machine. So the most easiest thing is just go on and just find the S, which is the apparent power, which is equal to 3 VI conjugate. So the conjugate, like you know before, is just, that means you replace, or just you switch the sign of the imaginary part of the current. So if the imaginary part is positive, you place it as negative. If it is negative, you place it as positive. So this will be 3V, which is 480, and angle 0, so yeah, it doesn't have an imaginary part. And multiply by I conjugate. I is minus 36.7 minus J18.8, so I will place it like positive J18.8. Why positive? Because it's how you find a conjugate. Okay, this conjugate, that's star, it means conjugate. That means you just switch the sign of the imaginary part. Fine. The P, which is the active power, is the real part of this. So yeah, once you find it, you just find it by the real part of the current. So just multiply 3 by 480 by 36.7. I'll give you this value here. And Q, the imaginary part, like you've seen here. So it'll be 3V by 18.8, which is the imaginary part, and it will give you this value here. The most important thing to look at is you look in here. The electric power, the active power P, is negative sign. Negative sign, that means just changing direction. Rather than just going inside the machine, it's going outside the machine, okay? Because that's a generator. But the Q is positive. That means the Q is going into the machine. And that's what we said about the induction generator. The induction generator gives P, gives useful power, active power to the grid, but takes reactive power from the grid. It's not like the same with synchronous machines. Synchronous machine, most of the time, if you remember, it's giving both. So the machine gives P and Q to the grid. But for the induction machine, like you see in here, it's given P but taking Q. So the P is negative. That means it's changing direction. It's not going into the machine. It's going outside of the machine to the supply, to the grid. But the Q is positive because still the induction machine requires reactive power to go into the machine to build its own magnetic field, because it does not have a separate winding with a separate source to build its own magnetic field. Okay, guys? Okay. Keep going this. He wants you to find him the air gap power. So to find air gap power, just like the usual equations we used, which is 3I2 squared R2 over S. Okay, that's why you need to calculate the current I2 just by using the current divider rule, because yeah, I1 is the total current. You just go with I1 and just multiply it by the JXM over R2 over S plus JX2 plus XM. And then you go around to find I2. You just need the magnitude of the current, because you know the power is just found by the magnitude of the current, not the magnitude and angle. Please do not forget this. So if you just calculate I2 here and find its magnitude, it will be 37.8. Again, I totally recommend to just use a calculator that's capable of doing the complex math directly, because if you want to do this by hand, it will take you ages. So I totally recommend this. So yeah, you can just find this current magnitude and just push it into this equation. I will give you the air gap power. Again, it's negative. Negative indicating it's just changing direction, rather than going into just from the air gap power. Usually for the motor mode, the air gap power is going from stator, so that is the stator side, and that is the rotor side. And the air gap power is going from stator to the rotor, because that's a motor. For here, it's a negative sign, and that's why it's just changing direction. It's now going from the rotor side to the stator side. And that's how a generator works. The input power is the mechanical power going to the rotor, and the output power is taken from stator as electricity. Okay, guys? So that's why the air gap power is negative now, because you're talking about a generator mode, not a motor mode. Okay? After this, I want you to calculate the torque. Like we know that torque is P air gap over omega S. Omega S is the synchronous speed, but in radian per second, so you just calculate it using this, or just easily omega S equals 2 pi over 60 multiplied by the synchronous speed. Synchronous speed, we already found it to be 1200. So you just find omega s from here. The torque will be negative also because air gap power is negative. That's the whole point. The torque is negative. Why? Because it's not like the other torques, okay? So the torque of the motor is just a result, is just the output. So the torque is something out of the machine, okay? Because that's a motor, and it's the torque, which is the mechanical torque of the machine, is just going out. That's a motor mode. But here, because that's a generator, it's a negative. That means the torque is changing direction. Rather than to being out of the machine, it's going into the machine. And that's how you deal with a generator, actually, because you need to put mechanical torque from an external mechanical source to the rotor to force the rotor to rotate. And that's why the torque is negative, because it's changing direction also, from being output to being input. Okay, guys? The same way, I'm gonna find the mechanical power output, okay, which is the shaft power, or the output power, will be P converted minus P rotational losses, P friction windage, So you just go and find P converted by finding P air gap multiplied by 1 minus S, just like we did before by the other induction motor stuff. So you go along with this. Don't forget this slip is now negative, so 1 minus S will be basically 1 plus the slip value, because the slip is negative. So you just do this, and you find the converter power to be also negative, and you just take out the rotation losses from it, and the output power will be negative. What I mean by output is negative, again, that means it's changing direction. Rather than to be an output power, the mechanical power, the shaft power, the mechanical power in the shaft, to be output in the motor mode, now it's negative. That means your shaft power, the mechanical power, is now input, not output. Okay, guys? That's why we just know how to calculate the efficiency will be the P output over P input. The P output here is the electric power, and the input power is the shaft mechanical power, because you know that's a generator. The output power is electricity, and the input power is mechanical. Okay, so P electrical is 53, which is we just calculated at the beginning, and the output, or sorry, the input is the mechanical power. We just found it here, which is 58.9. Okay, we'll totally take the negative actually, but yeah, both of them will be negative, so the two signs will just cancel out, and the efficiency will be 89.9%. So it's the same way we just solved the same problems of the equivalent circuit before with three-phase induction motors, but we're doing this with the generator mode. Your slip will be negative, and you just go the same way doing everything. But now you understand what's happening here, why everything is just changing sign because of changing direction, and why your reactive power, your Q, still positive here, because like we said, for induction generator cannot give Q to the grid, cannot output Q. It has to be still input Q to build its own magnetic field, because it doesn't have a separate winding to do it. Okay, guys? Okay, I hope that just help you just make it understanding more about the generator mode in this kind of machines. That's important to go along with this. Okay, the third and last mode, we didn't talk about other modes like this before. If you remember, with DC machine and synchronous machine, we always talk about a DC motor and a DC generator, a synchronous motor and a synchronous generator. We don't talk about a third mode of operation. So you'll find here for the induction machine a third mode of operation. We call it plugging mode. Okay, sometimes we call it braking mode. Okay, what is this? Let me talk about the plugging mode here. So we'll say that suppose an induction motor is running its motor now, yeah. So let me say it's induction motor, not to confuse you. So an induction motor, it's three-phase, obviously. Three-phase induction motor is running. Okay, so you have a motor is running in one direction. Okay, and an instant braking is required. Okay, So you don't have the time just to switch off the voltage and wait for the machine to just stop, or use mechanical plug, some sort of mechanical brake to try to just reduce the speed of the shaft of the motor. No, you want an instant braking. You want it to stop as fast as it can be. Okay, for this you can use plugging. This third mode we're talking about is used if you want to just instantly brake the machine. That's why we call it a braking mode. Okay, how do this? Simply reverse the connection of two phases of stator supply. Remember what this happened? If you switch any two phases of the three phases connected to the winding of the stator, like we said before, it will instantly reverse the direction of rotation of the magnetic field poles. If you remember when I talked to you about how to create a rotating magnetic field, I said the sequence controls the direction of rotation. So if you just reverse the connection of any two phases of them, okay, so it will instantly reverse the direction of rotation of the magnetic poles of this machine. Okay, so that's all happened. Reverse the connection of two phases of stator supply. That will instantly reverses the direction of rotation of the magnetic poles. I mean the synchronous speed. The synchronous speed will just be reversed. If it was this direction before, it will now instantly be in this direction. Okay, if it was clockwise, it will be now anti-clockwise, or vice versa. That will happen instantly. Why? Because it's saying that the synchronous speed, or the speed of the magnetic poles, it just comes from electricity. You know, the synchronous speed is 120 F over P. It's all coming from the frequency and the voltage just applied to the winding. Okay, so that's easy. It will instantly be reversed. But the problem is, for the motor mode, if you remember, because we are talking about a motor here, just rotating in some way, for the motor mode, with the synchronous speed like that, the mechanical speed of the rotor will be just following it, but in the same direction, but a little bit less. Okay? What you're trying to do now is, rather than having the synchronous speed in this direction, you will be instantly reversing it to go into this direction, so this going from here to there. What will happen for the mechanical speed? It should be also reversing direction to go like that. Okay? But could this mechanical speed be also instantly changing direction like the synchronous speed? You should know the answer, no. Okay? The rotor has inertia, okay? Because it has mass, it has weight into it. So Nm, the mechanical speed of the rotor, cannot be instantly reversed. Okay, it takes some time to reduce speed to 0 and switch direction. So what will happen is your motor will be just slowing down until it's 0, and then it will reverse direction of rotation going to the other way. Okay, so it will take some time to reduce speed to 0, and we'll switch direction to go back to motor mode, but in the reverse direction of rotation. Okay, that's how actually we can reverse the direction of any induction motor working. If the motor is just rotating clockwise and you want to make it rotate anti-clockwise, you just switch off the supply and change connection of any two phases, and the motor will start rotating again, but in the different direction. The whole point is, what if you do this while the motor is online? The motor is now rotating into some way and you just instantly switches two phases. And now the motor is required to reverse direction instantly, but it will not do this. It will be very hard braked, okay? Because you'll have just this synchronous speed is now reversing direction to go this way. So it will try to drag the rotor also in its direction, okay? So it will just cause like a brake on the motor. That's why we call some sort of an instant brake. But it will not be instantly, making that the motor will be braked in a zero time. No, it will take some time because still the motor has some inertia to it. Okay? But it will slow down to zero and then it will just switch direction and go into the other way. Okay, guys? That is what we call a plugging. So the period while the rotor is slowing down to zero speed before switching direction is called plugging mode. Okay, so yeah, you know now. So the motor is now, you just switch it two phases, so the synchronous speed has instantly changed direction, but the mechanical speed still didn't change direction, but it's slowing down until it just goes zero, and then it will change direction and go the same direction again with the synchronous speed, and that's fine. It's back to motor mode. But into this transient period, what will happen actually, your synchronous speed is going this way and your mechanical speed is going that way. Yeah, this mechanical speed is now reducing down bit by bit until it will go zero, and then it will try to go into the other direction like that. But before this happens, you still have some time while your synchronous speed is going into a direction and your mechanical speed into another direction. Okay, guys? So for this, we're going to calculate the slip, which is ns minus nm over ns. What will happen now is your mechanical speed and your synchronous speed are in two different directions. And that's why you're gonna put the mechanical speed here with a negative sign, because it's into a negative direction to the synchronous speed. And that's why the slip here is higher than 1. Why? Because what will happen here, it will basically have ns plus nm over ns. Why? Because nm is basically, you will have to put it as negative sign, because it is in the reverse direction compared to the synchronous speed. And that is the only mode you will find it like that. The slip is higher than 1. Most of the time, just for the motor mode or for the generator mode, the slip is always less than 1. But for the plug-in mode, you will find it to be higher than 1, because that is the only mode you will find the mechanical speed and synchronous speed are in reverse directions. For the motor mode, they are in the same direction, but nm is less than ns. For generator mode, they are in the same direction, but nm is higher than ns. But for the plugging mode, they are in reverse direction. Okay, guys? Again, it's some sort of a transient time. It will not last forever. It's just gradually reducing this until they catch up on the same direction again. But during this transient time, you still have this condition, that the synchronous speed and the mechanical speed are in two different directions. Okay, guys? Okay. So for this mode, if the machine is working like a motor or a generator, no, it's not a motor, it's not a generator. It's totally different mode. That's why it's the third mode of operation for a three-phase induction machine. Okay? If you want to just go look at the power flow diagram for this mode, the plugging mode, what will happen actually, that you have electric power coming, P electric, coming from the stator supply. Okay, you still connected to a three-phase voltage supply, so you have electricity going into the machine. The whole point is, you're not converting this into mechanical power output and now you are a motor. Actually, you have mechanical power also going into the machine. What is this mechanical power coming from? Coming from the inertia of moving parts. The rotor and the shaft and even the load connected, they are all have mass, so they are all have inertia. So the inertia of this load will be mechanical power even going into the machine also. And that's the weird thing about this mode. You have electric power and mechanical power, they are both going into the machine, and they are all translated into losses. That is copper losses in stator, core losses in both stator and rotor, both of them, copper losses in rotor, and rotational losses, obviously. Okay? So here you have electric power from the voltage source on stator and mechanical power from inertia of moving parts are together going input to the machine and will be converted into losses. So all the power, the electric power coming from the source and the mechanical power coming from the inertia of the moving part, will be translated into losses. And that's why it's not a good thing to be dealing with, because you'll have a massive power going into the machine as losses, so the machine will heat up. Okay? But fortunately, this situation just lasts for a very short amount of time, otherwise the machine will not be able to handle it. Okay? The whole point is, it's not a good thing to go with. Keep that in mind, guys. We do not do this unless we have a very small motor connected to a very small load. If you're talking about a big motor connected to a big load and you're trying to just instantly switch the direction of rotation of the motor, you most of the time will be sacrificing the shaft. The machine will be break, and we do not want to do this. Okay, so it's not a very safe mode to go with unless you have a very small motor connected to a very light load. So that's fine, the machine will handle. But if you have a big motor driving a big load, it's not a safe thing to go with and try to just instantly switch two phases of the motor to switch direction of the machine instantly. It's not something good. Okay, so by the way, remember when we talked about the torque speed characteristics of the machine? Remember that? So that was the torque speed characteristics of the motor. If you remember, it was just like that. Yeah, that is for the motor mode. But if you want to do this for the generator mode, how you find it? Remember, that was the synchronous speed. Yes, for the generator mode it will be the same something, but it going into negative like that. Why? Because the torque for the generator is negative. Remember, for the generator, like we just have the same problem we solved right now, the generator mode has a negative torque because the torque is just switching direction. Rather than to be an output, it will be input, because we need mechanical torque input to the machine to rotate it. Yeah, and the speed is higher than the synchronous speed, and that's why we just push it to this direction. For the generator, the speed is higher than the synchronous speed. But for the motor, the mechanical speed is less than the synchronous speed. Okay, but what about the plugging mode? The plugging mode, like we said, the slip is negative. That's why it's going to other direction, to this direction like that. It's not actually going straight, I'm sorry, just going a little bit down like that. So that is the plugging mode, because you have a negative slip. Okay, so that the complete torque speed characteristics of three-phase induction machine. That is the torque speed characteristics of three-phase induction machine. Not just for the motor mode like we had before, but now for the three modes of operation. That is the motor mode, that is the generator mode, and that is the plugging mode. You want to go with all of them on the same curve. Okay, guys? Okay. So that's the whole point to talk about here, is you have three modes of operation. The motor mode, well, that's the usual one, the most commonly used mode of operation for the induction machine, while you input electric power to the stator terminals, and now you have electricity going into the stator, and this will be converted into mechanical power on the rotor, and the rotor will start rotating. And like we said, the mechanical speed of the rotor will be a little bit less than the synchronous speed, but slips behind it. That means it's in the same direction of the synchronous speed. And that's why your slip will lie between 0 and 1. It's a small value most of the time, like we said before. And the power flow, just going from electric power on the stator to mechanical power, will be developed on the rotor, and you will lose some losses all over the way. For the generator mode, you're forcing the rotor to rotate higher than the synchronous speed, but you still have the voltage or the supply connected to the stator. Actually, this supply connected to the stator, while you'll just create electricity and push to the grid or to the supply connected to it. That's how the generator works, that you rotate the rotor and the electric power is being developed or generated into the stator and going to the outside world. But for here, your stator winding will act like two roles. It will be the armature winding, if you remember, the armature winding where you have the electricity have been generated on and pushed to the grid, but it will also act like your medium of having reactive power from the grid to feed your own magnetic field inside the machine, because like we said, we don't have a separate field winding here like we had before in the synchronous machines. Okay guys, actually for the generator mode also here you can deal with it as what we call a doubly fed induction machine, and it is the most commonly used one for wind turbines. What I mean by doubly fed machines is you have two three-phase voltage sources, one on the stator and one on the rotor, and that's why we call it doubly fed machine. It's not like we would call here. So the generator mode I mean here, we just have one voltage source applied to the stator and that's it. If you have another source applied to the rotor, now you have a totally different machine winding, which we call it the doubly fed induction machine. It's not a regular induction machine, while you have just a voltage source on the stator and the rotor gets its voltage by induction from the stator. Now we have a totally different machine. Yeah, it acts mostly like almost the same theory of operation, but it's different because you have two sources, one on the stator and one on the rotor. If you have a doubly fed machine like that, you can actually work it out to be having a Q output, because you have a different source now on the rotor that can build your magnetic field, okay? But for the regular machine mode we're talking about, you just have one source on the stator, so the stator still have to get some Q from the grid to build its own magnetic field. And that's why we're saying that. You will have P, electric power, the active power output to the grid, but Q still input from the grid to the machine to build its own magnetic field. So that's how you just deal with the power flow. You have mechanical power input to the rotor and you just lose some losses, and the rest will be converted to electricity on the stator. That is the active power flow, you know. But for reactive power, still have input to the machine if it's connected to the grid. It takes it from other synchronous generator connected to the grid, but if it is isolated, you just have some capacitors connected to the machine's terminals to build its own magnetic field. The third one for the plugging mode, and that happens if you try to instantly just brake the motor, reduce the speed down to 0 instantly and reverse its direction. So while the motor slows down to 0 before it just reverses direction, while this slowing down period, you have a very unique mode of operation, while your synchronous speed and mechanical speed are in different directions, and that will give you a slip higher than 1. For this mode, like we said, we'll have electric power coming from the source on the stator, and mechanical power coming from the inertia of the moving parts, which is the rotor and the shaft and the load connected to it. All of those will be translated into losses, and this will heat the machine up. But like we said, because it's a very small portion of time, the machine can handle it, but it's not that safe actually to do this. So we'll not go this as a standard braking way. So I'm asking you wanna just brake the machine, okay, just reduce its speed to 0, it's not a very safe way to go as plugging by just switching two phases of the machine. Most of the time we use mechanical brakes or something to just gradually reduce the speed of the shaft to a safer way to brake the machine. Okay guys? And that's the complete torque speed characteristics of three-phase induction machine for the motor mode, generator mode, and plugging mode. Okay? Okay. So that's all I want to talk to you about for three-phase induction machines. We started like any other kind of machine. We studied the construction of the machine for the stator and for the rotor for both the squirrel cage and wound rotor types. And we talked about the theory of operation, and while that we talked about the generation of rotating magnetic field out of a stationary three-phase winding by applying three-phase voltage to them, and we just find out how to do this. And then we understood the theory of operation of such a machine, of how you can generate it, or how the torque is developed. And then we found how to model it using the equivalent circuit, the per phase equivalent circuit, and use it to just predict the machine's performance. On the same way, we just used or just studied the lab experiments used for determination of the equivalent circuit parameters, so we can use this equivalent circuit to predict the motor performance. After that, we talked about the two very important topics, which is the speed control of three-phase induction motor using different ways of speed control, and with so much emphasis on the most popular one, which is the V/F speed control using power electronic converters. And we talked then about the starting of three-phase induction motor, which is the way of reducing the high amount of current drawn by the motor at the starting instant. And we talked about the totally different methods of doing this, and emphasizing on the most two important one, which is using soft starters by power electronic converters, and the Y delta starter, which is the most commonly used one. And after that, we just talked about the other modes of operation of the machine. So yeah, we dealt with the motor mode for the time, but we have to just talk about the other modes of operation for the generator mode and the plugging mode for this lecture. Okay, that's all I want to talk about. Three-phase induction motor is still, there is so much other details, and you have your recommended textbook if you want to go for further details of everything, but I'm very satisfied about the portion of the information we had about this very, very important kind of a machine to deal with. Okay, that's the end of my talking about three-phase induction motor, and in the next lecture I'll be start talking about other special machines. I'll be having just have two lectures talking about the single-phase induction machines, okay, and another lecture to talk about other special kind of machine, which is the stepper motors and switch reluctance motor. Just will have a very quick overview about those kind of machines to be more familiar with them. Okay, as usual, I'll be very happy to have your questions. Just email me and I'll be very happy to answer them. Thanks so much guys for joining me today, and I will be very happy to have you along on the next lecture.